Imagine waking up one morning and discovering that everything you thought you knew about human history was incomplete. Imagine learning that the story of our species did not begin in the caves of Africa or the fertile valleys of Mesopotamia, but on another world entirely. A world now cold, lifeless, and covered in rust-colored dust. That world is Mars. And if the evidence is correct, then we are not natives of Earth at all. We are refugees from a dying planet, carrying within us the genetic memory of a civilization that once looked up at a blue sky we can no longer remember. Stay with this thought until the end, because what follows challenges not only our understanding of where we came from, but who we really are. For as long as humans have gazed at the night sky, Mars has held a special place in our imagination. It is visible to the naked eye, glowing with a reddish hue that ancient cultures associated with blood, war, and fire. The Babylonians called it Nergal, after their god of death and pestilence. The Greeks named it Ares, their god of war. The Romans gave it the name we still use today, Mars, the god of battle. But beneath these mythological associations, there has always been something deeper, something that pulled at human curiosity in ways other planets did not. Mars felt familiar. It felt like it mattered. Even before telescopes, people sensed that Mars was different from the other wandering lights in the sky. It was not just a distant star or a gas giant beyond our reach. It was a world, a place with features we could almost recognize. When telescopes finally revealed its surface in greater detail, that feeling only intensified. Astronomers saw polar ice caps that grew and shrank with the seasons. They saw dark patches that seemed to change over time, suggesting vegetation, or perhaps even forests. They saw what appeared to be vast networks of straight lines crossing the surface, which some interpreted as canals built by an advanced civilization struggling to survive on a drying world. We now know those canals were optical illusions, tricks of light and shadow that fooled even trained observers. But the impulse behind that interpretation was not entirely wrong. Mars does tell a story of a world that once had water, that once had conditions suitable for life, and that slowly lost everything. The difference is that we no longer need to rely on blurry telescope images or imagination. We have sent machines to Mars. We have walked on its surface through rovers, analyzed its rocks, sampled its atmosphere, and mapped nearly every crater and canyon. And with each new discovery, the possibility that Mars was once alive grows stronger. More than that, the possibility that it was once our home becomes harder to dismiss. This is not science fiction. This is a question that emerges from real data, from patterns in geology, chemistry, and even biology that suggest a connection between Earth and Mars far deeper than we ever imagined. The question is not whether Mars could have supported life. The question is whether it supported us. To understand why this idea is even considered, we need to start with what we know about Mars itself. Not the Mars of today, which is a frozen desert with an atmosphere thinner than the edge of space, but the Mars of billions of years ago. A Mars that may have looked remarkably similar to the Earth we know now. When planetary scientists first began studying Mars in detail, they expected to find a dead world, a relic of cosmic violence with nothing to tell us except the history of impacts and erosion. What they found instead were the unmistakable signs of water. Not just a little water trapped as ice at the poles, but evidence of rivers that once flowed across the surface, lakes that filled ancient craters, and perhaps even oceans that covered vast stretches of the northern hemisphere. The evidence is carved into the landscape itself. Valley networks snake through the terrain, branching like the tributaries of rivers on Earth. Delta formations spread out where these rivers once emptied into standing bodies of water. Sedimentary layers stack upon each other in patterns that can only form when water deposits material over long periods of time. Even the minerals tell the story. Clays, sulfates, and carbonates are found across the Martian surface, and these minerals form only in the presence of liquid water. But water alone is not enough to make a planet habitable. Mars would also have needed warmth, and warmth requires an atmosphere thick enough to trap heat. Today, Mars has almost no atmosphere to speak of. The air pressure on the surface is less than 1% of Earth's, so thin that liquid water cannot exist in a stable form. It either freezes instantly or boils away. Yet the geological evidence shows that water was not just present, but abundant. This means Mars must have once had an atmosphere far thicker than it does now, an atmosphere capable of keeping the planet warm enough for rivers to flow and rain to fall. Scientists believe this atmosphere was lost gradually over billions of years. Mars lacks a global magnetic field, the invisible shield that protects Earth from the solar wind. Without that protection, the solar wind, a stream of charged particles constantly flowing from the sun, slowly stripped away Mars's atmosphere atom by atom. As the atmosphere thinned, the planet cooled. The rivers dried up. The lakes evaporated or froze. The once blue-green world turned into the red desert we see today. This process did not happen overnight. It took hundreds of millions of years, perhaps even longer. And during that time, during those long stretches when Mars still had water and air and warmth, life could have begun. Not just microbial life, though that would be extraordinary enough, but complex life, evolutionary life, life that could adapt, diversify, and perhaps even develop intelligence. On Earth, life appeared surprisingly quickly once conditions were favorable. Within the first billion years of our planet's existence, single-celled organisms had already emerged. Within another billion years, those cells had become more complex, eventually giving rise to multicellular life, plants, animals, and everything we see around us today. If Mars followed a similar timeline, and if it had several hundred million years of habitable conditions, then it too could have seen the emergence of complex organisms. The question is not whether life on Mars is possible. We already know it is. The question is how far that life progressed before the planet's decline made survival impossible. This is where the story begins to shift from planetary science to something more speculative, more unsettling. If Mars once had life, and if that life had time to evolve, then what happened to it when the planet began to die? Did it simply go extinct, leaving no trace except perhaps fossilized microbes buried deep beneath the surface? Or did it find a way to survive, to adapt, to escape? And if it escaped, where would it have gone? The answer, of course, is obvious. There was only one other world within reach, one planet that was moving in the opposite direction, growing warmer and wetter while Mars grew colder and drier. That planet was Earth. And this brings us to the central question of this entire exploration. If life existed on Mars, and if it somehow made the journey to Earth, then we are not Earthlings at all. We are Martians. We are the descendants of a world that came before, carrying within us the legacy of a planet we no longer remember. To understand how life could have traveled from Mars to Earth, we need to explore a concept that was once dismissed as fantasy, but is now taken seriously by scientists. It is called panspermia, the idea that life does not originate independently on every planet, but can spread from one world to another, carried through space by natural processes. The mechanism is simpler than it sounds. When a large asteroid or comet strikes a planet with enough force, it does not just create a crater. It blasts fragments of rock and debris into space, some of which escape the planet's gravity entirely. These fragments, ejected at high velocity, travel through the solar system for thousands or even millions of years before eventually falling onto another world. We know this happens because we have found Martian meteorites on Earth. These are rocks that were once part of Mars, blasted into space by ancient impacts, and that eventually landed on our planet. Scientists can identify them by analyzing their chemical composition and comparing it to samples studied by Mars rovers. So far, more than 200 Martian meteorites have been found on Earth, proof that material can and does travel between the two planets. But these meteorites are not just rocks. They are potential carriers of life. When an impact occurs, fragments near the surface can be ejected before they are sterilized by heat. If microorganisms were present in the soil or rock at the moment of impact, they could be launched into space still alive, protected within the stone. Once in space, these organisms would face extreme conditions: freezing temperatures, vacuum, and intense radiation. Most would die. But some microbes are extraordinarily resilient. Studies have shown that certain bacteria can survive in space for years, entering a dormant state that allows them to endure conditions that would kill almost any other form of life. When a meteorite eventually crashes onto another planet, the organisms inside could potentially survive the impact if the rock does not heat up too much during entry. Laboratory experiments have demonstrated that microbes embedded in stone can survive shock pressures and temperatures that simulate meteorite impacts. If even a few cells survived the journey from Mars to Earth, they could have seeded our planet with life. This is not speculation. This is a scientifically plausible mechanism for how life might transfer between worlds. But the implications go far beyond microbes. If simple life could travel from Mars to Earth, then the possibility arises that more complex organisms, or at least the genetic material from more complex organisms, could have made the journey as well. DNA is remarkably stable under the right conditions. It can survive for thousands of years in frozen or desiccated environments. If Martian life had evolved to the point of having complex genetic structures, and if fragments of that life were ejected into space during an impact, then Earth could have received not just living cells, but blueprints, genetic instructions that influenced the development of life on our own planet. This leads to a startling possibility. What if the evolutionary tree of life on Earth did not begin from scratch? What if it was seeded, jump-started by genetic material that arrived from Mars? The early Earth was a hostile place, bombarded by asteroids, covered in oceans with no continents, and lacking the stable environments that complex life requires. But if life had already evolved on Mars during a more stable period, and if that life was transferred to Earth, then our planet could have inherited a head start, receiving organisms or genetic material that had already undergone millions of years of evolution. This would mean that life on Earth is not entirely native. It is Martian in origin. And if that is true, then so are we. The idea that humans might be descended from Martian life sounds like science fiction, but it is rooted in a logical chain of reasoning. If Mars was habitable before Earth, and if life began there first, and if that life was transferred to Earth through panspermia, then everything that evolved on Earth afterward, including us, would carry that Martian heritage. We would be the distant descendants of organisms that first emerged under a red sky, billions of years ago. But there is another layer to this theory, one that is even more provocative. What if the transfer was not just biological, but intentional? What if a Martian civilization, facing the collapse of their world, found a way to send not just microbes, but something more? Information, technology, or even themselves. This brings us into territory that mainstream science does not accept, but that is worth exploring because of what it implies about human history. If a civilization once existed on Mars, and if they understood their planet was dying, they would have faced a choice: stay and perish, or find a way to survive elsewhere. Earth would have been the obvious destination. It was close, it was growing more habitable, and it offered the one thing Mars no longer could: a future. But how would they have made the journey? Interplanetary travel, even with advanced technology, is not simple. The distance between Mars and Earth varies depending on their orbits, but at its closest, it is still over 50 million kilometers. Building spacecraft capable of that journey would require resources, energy, and time that a dying civilization might not have. Yet the possibility cannot be dismissed. If Martians reached even a fraction of our current technological level, they would have understood the principles of rocketry, orbital mechanics, and life support. They could have built ships, slow and primitive by our standards perhaps, but functional enough to carry a small population across space. There is no physical evidence of such ships, of course. No ruins on Mars, no wreckage in orbit, no ancient spacecraft hidden on Earth. But absence of evidence is not evidence of absence, especially when we are talking about events that occurred billions of years ago. Any structures, any technology, Any sign of their presence would have been erased by time, buried under dust on Mars, or worn away by erosion on Earth. What might remain, however, is something far more subtle. If Martians came to Earth, they would not have arrived as conquerors. They would have been survivors, refugees from a collapsing world, arriving on a planet already teeming with primitive life. Their numbers would have been small, their technology failing, their resources exhausted. They could not have built cities or maintained their civilization, but they could have integrated. They could have interbred with the native hominid species that were beginning to emerge on Earth, passing on not just their genes, but traits that would set certain lineages apart. This could explain some of the mysteries in human evolution. Why did humans develop such large brains so quickly compared to other species? Why do we have traits that seem almost out of place for purely earthly evolution, such as our poor adaptation to Earth's gravity, which causes chronic back pain, or our sensitivity to sunlight, which damages our skin far more than it does other mammals? Why do human infants have such difficulty being born compared to other primates, requiring assistance that no other species needs? Some researchers have pointed to these anomalies as evidence that humans are not entirely native to this planet. They argue that we are adapted to conditions slightly different from Earth's, conditions that might have existed on a planet with lower gravity, a different atmospheric composition, or a dimmer sun. A planet, in other words, like Mars. These ideas are not accepted by mainstream science, and for good reason. Evolution explains human traits through natural selection and environmental adaptation over millions of years. Our back pain comes from our recent evolutionary shift to upright walking. Our sensitivity to sun is explained by our loss of fur. The difficulty of human birth is due to the size of our brains relative to the birth canal. There are rational explanations for all of these traits that do not require invoking a Martian origin. But what if those explanations are incomplete? What if there is a hidden variable, a piece of the puzzle we have not yet considered? If a small population of Martians interbred with early hominids, their genetic contribution might be subtle, spread thin across millions of generations. We would not see obvious alien features. We would see traits that seem almost human, but not quite. Characteristics that make us unique among Earth's species in ways that are hard to fully explain. And this brings us to one of the most intriguing aspects of this theory. If Martians came to Earth and integrated with native populations, they might have brought more than just genes. They might have brought knowledge. Not written records or advanced technology, which would have decayed long ago, but something more enduring. Cultural memory. Stories passed down through generations. Myths that preserve fragments of truth about a world that came before. When we look at ancient human cultures from around the world, we find recurring themes that are difficult to explain. Stories of gods descending from the sky, legends of a lost homeland, a paradise that was destroyed, myths of a great flood, a catastrophe that wiped out an earlier civilization, tales of beings who came from the stars and taught humanity the secrets of agriculture, mathematics, and astronomy. These stories exist in cultures that had no contact with each other, separated by oceans and thousands of years. Why do they share such similar themes? The standard explanation is that humans everywhere face similar challenges and create similar myths to explain natural phenomena. Flood myths, for example, are common because floods are universal disasters that every culture experiences. Sky gods are common because the sky is a shared feature of human experience. But what if there is another explanation? What if these myths are not invented, but remembered? What if they preserve fragments of actual events, passed down through oral tradition for so many generations that they have become distorted, transformed into legend, but still carrying a core of truth? If Martians came to Earth, the arrival itself would have been traumatic. Imagine the impact, literal and metaphorical, of beings from another world appearing among primitive human tribes. They would have seemed like gods, possessing knowledge and abilities far beyond anything the natives had seen. Even if the Martians had lost most of their technology, even if they were dying and desperate, they would still have known things that early humans did not. They would have understood the stars, the cycles of planets, the principles of agriculture and metalworking. They might have taught these skills to the tribes they encountered, not out of benevolence, but out of necessity, trying to establish a foothold in this strange new world. Over time, as the Martians died out and their descendants interbred with native populations, the memory of their origin would fade. But it would not disappear entirely. It would become myth. The story of gods who came from the sky, the memory of a lost world, a red planet where their ancestors once lived. The knowledge they brought, agriculture, astronomy, mathematics, would be attributed to divine gift rather than interplanetary refugees. And the great catastrophe, the reason they left Mars, would become the story of a flood, a fire from the sky, a paradise lost. This interpretation is, of course, speculative. There is no direct evidence that ancient myths are distorted memories of Martian contact, but the parallels are striking enough to make us wonder. Why do so many cultures speak of a time before time, a golden age when gods walked among humans? Why do ancient astronomical traditions show knowledge of planetary cycles and celestial mechanics that should have been impossible without advanced instruments? Why do structures like the pyramids, built thousands of years ago, demonstrate mathematical and engineering precision that seems out of place for supposedly primitive societies? Mainstream archaeology explains these achievements through human ingenuity and gradual accumulation of knowledge. And most of the time, that explanation is sufficient. But there are anomalies. There are moments in history where progress seems to leap forward inexplicably, where civilizations develop capabilities far beyond what we would expect for their level of technological development. The construction of the Great Pyramid, for example, required an understanding of geometry, astronomy, and engineering that would not be matched again for thousands of years. The Antikythera mechanism, an ancient Greek device that calculated astronomical positions with astonishing precision, was so advanced that nothing comparable appeared again until the Renaissance. The Nazca lines, massive geoglyphs carved into the desert floor in Peru, are only fully visible from the air, raising the question of why a culture with no flight technology would create them. These are not proof of Martian intervention. They are proof that ancient humans were far more capable than we often give them credit for. But they also leave room for questions. What if some of this knowledge did not develop independently? What if it was inherited, passed down from a time when beings with advanced understanding walked among us? If we take this possibility seriously, then we need to ask where else we might find evidence. If Martians came to Earth, they would have left traces, not in the form of intact spacecraft or technology, but in subtler ways. Genetic anomalies, biological markers that do not quite fit the evolutionary tree, structures or artifacts that seem out of place in the archaeological record. Let us start with genetics. Modern DNA analysis has revealed that all humans share a common ancestry, but it has also revealed mysteries. There are sections of human DNA that do not have clear evolutionary origins. Non-coding regions, sometimes called junk DNA, that make up the majority of our genome. For years, scientists assumed these regions were simply evolutionary leftovers, remnants of ancient genetic experiments that no longer serve a purpose. But recent research suggests that some of these regions may be more important than we thought. They regulate gene expression, influence development, and may even carry information that we do not yet understand how to read. What if some of these mysterious regions are not evolutionary accidents, but inherited fragments from a non-earthly source? If Martian DNA, assuming it was similar enough to Earth DNA to allow interbreeding, entered the human gene pool, it might show up as anomalies, sequences that do not fit neatly into the evolutionary history we have constructed. These sequences would be diluted over millions of years, mixed and recombined with native DNA until they were almost unrecognizable. But they might still be there, hidden in plain sight, waiting for someone to look at them with the right perspective. Another place to look is in the archaeological record. If Martians arrived on Earth, they would have needed to land somewhere. They would have brought tools, materials, perhaps even biological samples. Over time, these would decay, But certain materials, particularly metals or ceramics, can survive for extremely long periods. There have been occasional discoveries of artifacts that do not fit neatly into established timelines. The Baghdad battery, for example, is a clay jar found in Iraq that some researchers believe may have been used as an ancient electrical cell, though this interpretation is disputed. The Piri-Reis map, drawn in the early 16th century, appears to show the coastline of Antarctica with remarkable accuracy, even though Antarctica was not officially discovered until 300 years later. The Saqqara bird, an ancient Egyptian wooden artifact, has a shape strikingly similar to a modern glider, raising questions about whether ancient peoples understood principles of aerodynamics. These objects are controversial. Most archaeologists explain them through conventional means, arguing that the Baghdad battery was simply a storage vessel, that the Piri-Reis map was based on earlier sources now lost, and that the Saqqara bird was just a toy or ceremonial object. But the fact that these objects exist at all, and that they continue to provoke debate, suggests that our understanding of ancient capabilities may be incomplete. If even a fraction of these anomalies turned out to have unconventional origins, it would force us to reconsider what we think we know about human history. Then there is the question of Mars itself. If a civilization once existed there, and if they left to come to Earth, what remains on Mars today? The answer, most likely, is almost nothing. The surface of Mars has been scoured by wind and radiation for billions of years. Any structures, any cities, any sign of habitation would have been worn down to dust long ago. But not everything would be gone. Certain materials, particularly those buried underground or sheltered in caves, could survive for immense periods of time. If we wanted to find evidence of a Martian civilization, we would need to dig. We would need to explore beneath the surface, looking for layers of sediment that might contain artifacts, fossils, or chemical signatures of industrial activity. So far, our exploration of Mars has been limited. Rovers have scratched the surface, analyzed rocks, and drilled a few centimeters into the ground. Orbiters have mapped the planet from above, revealing geological features but not the fine details that would indicate past life or civilization. We have only just begun to explore, but there are hints, features on Mars that do not quite fit natural explanations. The face on Mars, as discussed earlier, turned out to be a natural formation, but it sparked interest for a reason. There are other structures, pyramidal shapes, geometric patterns, and formations that some researchers argue look too regular to be entirely natural. The scientific community dismisses most of these claims, attributing the features to pareidolia, the human tendency to see patterns where none exist. And they are probably right. But until we explore Mars more thoroughly, until we send humans there to investigate on the ground, we cannot say with absolute certainty that every strange formation is natural. There is also the question of subsurface ice. Recent discoveries have shown that Mars has vast deposits of water ice just below the surface, particularly near the poles. If a Martian civilization once existed, they might have retreated underground as the surface became uninhabitable, building settlements near these ice deposits. Such structures, if they exist, would be invisible from orbit and could only be discovered through excavation or ground-penetrating radar. The possibility that ruins lie beneath the Martian surface is tantalizing. It suggests that the answers we seek are not on the surface, but hidden below, waiting for us to dig deep enough to find them. This brings us to the most unsettling part of the theory. If humans are descended from Martians, then Earth is not our original home. We are living on a planet that we adapted to, not one we were made for. This might explain why we have always felt a strange pull toward the stars, why we build rockets and dream of colonizing other worlds. It is not just curiosity, it is something deeper. A genetic memory of a time when our ancestors looked up at the sky and saw not wonder, but escape. Mars was dying, and they fled. Now we stand on Earth, and we feel the same restlessness. We know on some unconscious level that staying in one place is dangerous. We know that worlds can die, and so we reach outward, not just to explore, but to survive. If this theory is correct, then the drive to return to Mars, to explore and colonize it, is not just scientific ambition. It is a homecoming. We are returning to the world we came from, even if we do not consciously remember it. The red planet calls to us because it is written into our DNA, a distant echo of a time when our ancestors walked beneath a red sky. Some researchers have pointed to the strange coincidences in human psychology and culture that seem to align with this idea. The color red, for example, has always held special significance in human societies. It is the color of blood, of life, of power. But it is also the color of Mars. In ancient times, Mars was called the blood star, associated with war and death. What if that association is not just symbolic, but a memory? A deep cultural recollection of a red world that was once home. A world that became synonymous with loss and endings because it was the world our ancestors had to leave behind. Then there is the recurring theme in human mythology of a lost golden age, a paradise that was destroyed. Nearly every culture has some version of this story. The Greeks spoke of the age of Kronos, a time of peace and abundance before the gods fell into conflict. The Bible speaks of the Garden of Eden, a perfect world from which humanity was expelled. Hindu texts describe cycles of creation and destruction, where entire worlds rise and fall. Indigenous cultures around the world have stories of a time when people lived in harmony with nature before some catastrophe forced them to start over. These myths are usually interpreted as allegories, moral lessons about human nature, or explanations for why life is difficult. But what if they are more than that? What if they are fragmented memories of an actual event, the loss of Mars and the migration to Earth? The details would have been distorted over thousands of generations, transformed into symbolic language, but the emotional truth remains. We came from somewhere else. We lost that place, and we have been trying to reclaim it ever since. If this is true, then the next question is, what does it mean for us now? If we are Martians, if Earth is not our original home, does that change anything about how we live, how we see ourselves, or how we approach the future? In a practical sense, it might not change much. Whether we evolved on Earth or inherited our genes from Mars, we are still human. We still face the same challenges, the same need for food, water, and shelter, the same struggles with conflict, inequality, and environmental destruction. But in a philosophical sense, it changes everything. It reframes human history not as a story of isolated development on a single planet, but as part of a larger cosmic narrative. We are not Earthlings who dream of the stars. We are star travelers who forgot where we came from. And this perspective has implications for how we think about our future. If Mars was once habitable and then died, it is a warning. Planets are not eternal. They do not remain hospitable forever. Earth, too, will eventually become uninhabitable, whether through natural processes like the aging of the sun or through our own actions like climate change. If we are the descendants of Martians who fled a dying world, then we carry within us the knowledge, even if it is unconscious, that survival means leaving. We cannot stay in one place forever. We must become a spacefaring species, not just for exploration, but for survival. The drive to return to Mars, to terraform it, to make it habitable again, takes on a different meaning in this context. It is not colonization of a foreign world, it is reclamation of a lost home. If Martians once lived there, and if we are their descendants, then restoring Mars is not just a scientific achievement. It is a completion of a journey that began billions of years ago, when our ancestors left that world behind. But there is also a darker possibility. If a Martian civilization existed and failed, if they destroyed their planet through war, environmental collapse, or some other catastrophe, then we need to learn from their mistakes. The silence of Mars, the fact that no trace of them remains, is a warning. Civilizations can disappear. They can rise, flourish, and then vanish so completely that even their existence becomes a question mark. We are at a similar crossroads now, humanity has reached a level of technological development where we have the power to alter our planet on a global scale. Climate change, nuclear weapons, artificial intelligence, all of these carry existential risks. If we are not careful, we could follow the same path as Mars, leaving behind a world that future visitors will look at and wonder whether anyone ever lived here. The key difference is that we have the knowledge to avoid that fate. We can study Mars, learn what happened there, and make sure we do not repeat the same mistakes. Whether or not humans are literally descended from Martians, Mars is still our mirror. It shows us what a planet looks like when it loses its atmosphere, its water, its ability to sustain life. It is a warning written in geology, and we need to pay attention. This brings us to the final part of the story, the part where we look not backward, but forward. If Mars was our past, what does that mean for our future? And what will we find when we finally return? The question of whether humans will return to Mars is not if, but when. Multiple space agencies, along with private companies, are working toward the goal of sending humans to the Red Planet within the next few decades. NASA, SpaceX, the European Space Agency, and China all have plans for manned missions. The technology is advancing rapidly. Rockets are becoming more powerful, life support systems more reliable, and our understanding of how to survive in space more sophisticated. Within the next 20 to 30 years, it is likely that humans will walk on Mars for the first time. But this return is not just about planting a flag or conducting scientific experiments. It is about answering questions that have haunted us for centuries. Was Mars once alive? Did it support civilizations? And if so, what happened to them? When astronauts finally land on Mars, they will have the opportunity to explore in ways that rovers cannot. They will be able to dig deeper, analyze more thoroughly, and search for evidence that machines might miss. If artifacts exist, if ruins lie buried beneath the dust, humans will be the ones to find them. And if we discover even the smallest trace of a past civilization, it will change everything. It will confirm that we are not alone in the universe, that intelligence has arisen on other worlds, and that our story is part of a larger cosmic pattern. But it will also raise troubling questions. If a Martian civilization existed and then disappeared, what caused their downfall? Was it environmental collapse, war, a natural disaster, or something else entirely? And most importantly, could the same thing happen to us? These questions are not just academic. They have immediate relevance to the challenges we face today. If Mars teaches us anything, it is that planets are fragile. Atmospheres can be lost, climates can shift, oceans can vanish, life, even intelligent life, can be erased. Earth is not immune to these dangers. We are already seeing the effects of climate change, the loss of biodiversity, the depletion of resources. If we do not act, Earth could follow the same trajectory as Mars, slowly becoming less habitable until it is too late to reverse the damage. The return to Mars, then, is not just about exploration. It is about survival. It is about understanding the forces that shape planets and learning how to protect our own. It is about confronting the possibility that we are the descendants of a species that once faced extinction and found a way to survive by starting over on a new world. And if that is true, then we have a responsibility to ensure that history does not repeat itself. We must learn from Mars. We must understand what went wrong, and we must make sure that Earth does not become another dead world, another silent planet where future explorers will land and wonder whether anyone ever lived there. This is the deeper meaning behind the theory that Mars was humanity's first home. It is not just about where we came from, it is about where we are going. If we are Martians, then our journey is not over. It has only just begun. And this journey is not just physical, but existential. When humans finally stand on the surface of Mars, looking at the horizon where rust-colored dust meets a salmon-pink sky, they will be standing on ground that may hold the answers to our deepest questions. Not just scientific questions about geology or climate, but philosophical questions about identity, origin, and purpose. The very act of returning to Mars, if it truly was our ancestral home, carries symbolic weight that goes beyond exploration. It is a confrontation with our own forgotten past, a reckoning with a history that was erased by time and distance. Every rock sample analyzed, every drill core extracted, every subsurface scan performed will be searching not just for signs of ancient microbial life, but for evidence of ourselves, for proof that the story of humanity is far older and stranger than we ever imagined. But there is another dimension to this return that often goes unspoken. If Mars was once inhabited by a technological civilization, and if that civilization faced collapse, then Mars itself is not just a scientific laboratory, it is a crime scene. Or perhaps more accurately, it is an archaeological site where the evidence of what happened has been weathered away by billions of years of erosion, leaving only the faintest traces for us to interpret. When detectives investigate a cold case, one that is decades or centuries old, they work with fragmentary evidence. A bone fragment here, a fiber there, chemical traces that suggest what might have occurred. The challenge is reconstructing events from these scattered pieces, building a narrative that fits the facts, while acknowledging how much has been lost to time. Mars presents the same challenge, but on a geological timescale. If a civilization existed there 3 billion years ago, during the period when Mars was warm and wet, then everything they built, every city, every monument, every piece of technology, has had 3 billion years to decay. That is an almost incomprehensible amount of time. On Earth, we struggle to find intact artifacts from 10,000 years ago. Stone structures survive, but even they erode. Metals corrode. Organic materials vanish entirely. After 1 million years, almost nothing recognizable would remain. After 1 billion years, even the most durable materials would be ground to dust, scattered by wind, buried under layers of sediment, or sublimated into the thin atmosphere. So when we talk about finding evidence of a Martian civilization, we are not talking about discovering intact buildings or machines. We are talking about finding anomalies, chemical signatures that do not fit natural processes, isotope ratios that suggest artificial nuclear reactions, mineral deposits that show evidence of smelting or refinement, geometric patterns in the subsurface that are too regular to be natural. These would not be obvious. They would require sophisticated analysis, careful comparison with known natural processes, and a willingness to consider unconventional explanations when conventional ones fall short. The scientific community, understandably, is cautious about such claims. Science advances through skepticism, through demanding extraordinary evidence for extraordinary claims. And the claim that Mars once hosted a technological civilization is about as extraordinary as it gets. But caution should not become closed-mindedness. There is a difference between healthy skepticism and reflexive dismissal. If we approach Mars with the assumption that nothing artificial could possibly exist there, we might miss the very evidence we are looking for. We need to be open to possibilities while remaining rigorous in our methods. This balance is difficult to maintain, especially when the implications are so profound. Consider what it would mean if we found definitive proof of a past Martian civilization. Not ambiguous rock formations or questionable artifacts, but something undeniable. Perhaps a subsurface chamber discovered by ground-penetrating radar, its walls too smooth and regular to be natural. Perhaps a layer of enriched uranium or plutonium in sedimentary rocks, suggesting the use of nuclear technology. Perhaps, most dramatically, an intact facility or vault, deliberately buried to survive the ages, containing artifacts, data storage, or even biological samples preserved in stasis. Such a discovery would be the most significant in human history. It would answer the question of whether we are alone, not just in the present, but across the entire span of time. It would prove that technological civilizations can arise on multiple worlds, that the emergence of intelligence is not a cosmic fluke, but a natural outcome given the right conditions. It would vindicate those who have long argued that the universe is far stranger and more populated than mainstream science acknowledges. But it would also raise immediate and pressing questions. If Martians existed, what were they like? Did they resemble us physically, or were they entirely different forms of life? Did they have culture, art, philosophy? Did they struggle with the same problems we face? Inequality, conflict, environmental destruction? And most urgently, what killed them? Was it a slow death as their planet lost its atmosphere, or something faster and more catastrophic? These questions would not be merely historical curiosities. They would have direct relevance to our own survival. If we could understand what led to the fall of Martian civilization, we might be able to avoid the same fate. This is why the search for evidence on Mars is not just about satisfying curiosity. It is about learning from the past to protect the future. Now let us consider the possibility that the connection between Mars and Earth goes beyond simple panspermia, beyond the accidental transfer of microbes on meteorites. What if the transfer was deliberate? What if a dying Martian civilization, recognizing that their world was becoming uninhabitable, took active steps to ensure their legacy would survive? This moves us into more speculative territory, but it is worth exploring because it addresses a fundamental question. If you knew your civilization was doomed, if you knew your planet was dying and there was no way to save it, what would you do? One option would be to accept extinction, to let your species fade into oblivion as your world turned cold and lifeless. But that seems unlikely for any intelligent species, especially one capable of understanding astronomy and planetary science. They would have looked at the night sky and seen Earth, a nearby world that was growing more hospitable even as their own world declined. Earth would have been visible from Mars, a bright blue-white star that would have been studied with whatever telescopic technology they possessed. They would have observed its thick atmosphere, its abundant water, its stable climate. They would have known, or at least hoped, that it could support life. So the question becomes, could they have reached it? Interplanetary travel is not trivial, even for an advanced civilization. It requires sophisticated engineering, vast resources, and a deep understanding of physics and orbital mechanics. But it is not impossible. Humans, with only a few decades of serious rocket development, have already sent dozens of probes to Mars. We have landed rovers, flown helicopters, and even returned samples. Within a few decades, we expect to send humans there. If we can accomplish this much in less than a century of spaceflight, what could a civilization with thousands or millions of years of development achieve? The answer depends on how long Martian civilization had to develop. If they emerged during the period when Mars was warm and wet, roughly 3 to 4 billion years ago, and if they had even a few 100,000 years of technological development before conditions became untenable, they could have reached a level of capability far beyond our own. They might have built not just primitive rockets, but sophisticated spacecraft capable of carrying large populations across interplanetary distances. They might have established colonies on multiple worlds, spreading throughout the inner solar system to maximize their chances of survival. Earth would have been the most obvious target, but they might also have tried to settle on moons, asteroids, or other planets. Of course, establishing a colony on a distant world is far more difficult than simply reaching it. You need life support systems that can function for years or decades. You need a way to produce food, recycle air and water, and protect against radiation. You need enough people to establish a viable breeding population, which means hundreds or thousands of individuals at minimum. For a dying civilization with dwindling resources, assembling even a single mission of this scale would be an enormous challenge. It might represent the last desperate act of a species facing extinction, throwing everything they had into one final attempt to survive. If they succeeded, if even one ship reached Earth and landed successfully, the occupants would have faced a world utterly unlike the one they left behind. Earth 3 billion years ago was a harsh place. The atmosphere was different, with far less oxygen than it has today. The continents were smaller and less stable. Life existed, but it was primitive, consisting mostly of single-celled organisms and simple bacterial mats. There were no plants, no animals, no complex ecosystems. For Martians adapted to their own world, Earth would have been alien and hostile. but it was alive, and it was warm, and it had water. That would have been enough. Survival in such an environment would have required extraordinary adaptability. The Martians could not simply step out of their ship and breathe the air or eat the native life. They would have needed sealed habitats, technological life support, and ways to produce their own food. But technology fails. Equipment wears out. Resources run out. Unless they could establish a self-sustaining presence, their colony would eventually fail, leaving them to die on this strange new world, just as surely as they would have died on Mars. But there is another possibility, one that is both more plausible and more disturbing. What if survival did not mean maintaining their original form, but adapting to the new environment through biological modification? Modern humans are just beginning to explore the possibilities of genetic engineering. We can edit DNA, create organisms with novel traits, and even discuss the possibility of modifying humans to survive in extreme environments. A Martian civilization, especially one facing extinction, would have had powerful motivation to develop such technologies. They might have engineered themselves to breathe Earth's atmosphere, to digest Earth's primitive life forms, to tolerate Earth's higher gravity and different day length. These modifications would not have been optional. They would have been necessary for survival. Over generations, the modified Martians would have diverged further and further from their original form, adapting to Earth, interbreeding with whatever native life was compatible, until eventually they were no longer recognizably Martian. They would have become something new, something that fit this world. They would have become Earthlings. If this happened, then the question of whether humans are descended from Martians is not about a direct lineage, but about genetic contribution. We would not be pure Martians, but hybrids, carrying within us fragments of a genetic heritage that came from another world. Most of our DNA would be Earth native, the result of billions of years of evolution on this planet. But some fraction, perhaps a small but crucial fraction, might be Martian in origin. This fraction might be responsible for some of the traits that make humans unique among Earth's species. This brings us back to those curious anomalies in human biology and behavior that some researchers have pointed to as evidence of non-earthly origin. Let us examine these more carefully, not as proof, but as patterns worth investigating. First, there is the issue of human vulnerability to sunlight. Humans are unusual among mammals in our susceptibility to sun damage. Our skin burns easily, developing painful sunburn after relatively brief exposure. Prolonged sun exposure increases our risk of skin cancer dramatically. We need to wear protective clothing and apply chemical sunscreens to avoid damage from radiation that most other animals tolerate without difficulty. Why would evolution produce a species so poorly adapted to the primary source of light and warmth on our planet? The standard explanation is that humans lost most of their body hair relatively recently in evolutionary terms, and our skin has not yet fully adapted to the increased exposure. But Mars, being farther from the sun, receives only about 43% as much solar radiation as Earth. If humans inherited genetic traits from Martian ancestors adapted to lower light levels, it might explain our unusual sensitivity. We would be, in a sense, built for a dimmer sun. Second, there is the problem of gravity. Earth's gravity causes chronic problems for humans that other species do not seem to experience to the same degree. Back pain is nearly universal in human populations, affecting up to 80% of people at some point in their lives. This is typically attributed to our relatively recent evolution of upright posture, which puts stress on the spine. But Mars has only 38% of Earth's gravity. A species that evolved on Mars would have developed under much lighter gravitational stress. If Martians came to Earth, they would have experienced our gravity as crushing, forcing adaptations that might never have been fully successful. The chronic back problems that plague humanity might be a legacy of bodies designed for a lighter world, trying to cope with a heavier one. Third, there is the difficulty of human childbirth. Compared to other mammals, human birth is exceptionally difficult and dangerous. The infant's head is so large relative to the birth canal that delivery often requires assistance, and historically, childbirth has been one of the leading causes of death for women. The standard explanation focuses on the trade-off between large brains and the constraints of a pelvis adapted for upright walking. But if humans carry genetic heritage from a species that evolved under lower gravity, the problem might be compounded. A larger skull that would have been manageable on Mars becomes a critical liability on Earth, where everything is heavier and skeletal structures must be more robust. Fourth, there is our circadian rhythm, the internal biological clock that regulates our sleep-wake cycle. For most humans, the natural circadian period is not exactly 24 hours, but slightly longer, averaging about 24.5 hours. This means that in the absence of external cues like sunlight, humans tend to drift toward a longer day. Multiple studies have confirmed this pattern. Why would evolution produce an internal clock that does not match the length of Earth's day? Mars, interestingly, has a day length of 24 hours and 37 minutes, much closer to the human circadian average. If our biological rhythms were inherited from Martian ancestors, this mismatch would make sense. We would be carrying within us a clock set for a different world, one that rotates just a bit more slowly than the Earth we live on now. These anomalies are not proof of anything. Each one can be explained through conventional evolutionary theory without invoking a Martian connection. But taken together, they form a pattern that is at least curious. They suggest that humans are not perfectly adapted to Earth, that there are aspects of our biology that seem slightly out of sync with our environment. Whether this is due to Martian heritage or simply the messiness of evolution, which rarely produces perfect adaptations, remains an open question. But it is a question worth asking. Beyond biology, there are psychological and cultural patterns that also seem suggestive. Humans have always been explorers, driven by a restless urge to see what lies beyond the horizon. This trait has pushed us to every corner of the Earth, from the Arctic to the Amazon, from mountain peaks to ocean depths. We explore not just for resources or survival, but for the sake of exploration itself. We want to know what is out there. This drive is unusual among species. Most animals are territorial, staying within familiar ranges where they know the resources and dangers. Venturing into unknown territory is risky, offering little immediate survival advantage. Yet humans have always done it, even when it meant facing starvation, disease, and death. Why? One possibility is that this drive is a residual instinct from a species that had to leave their homeworld to survive. If Martian civilization faced extinction, the individuals most likely to survive would have been those willing to take enormous risks, to venture into the unknown, to try something that had never been done before. Those who stayed behind, who clung to the familiar, would have perished. Those who left, who embraced uncertainty, would have carried their genes forward. If we are descended from those risk-takers, then our restlessness, our need to explore, might not be a random quirk of human psychology. It might be a survival trait inherited from ancestors who had no choice but to leave everything behind and start over on a new world. This would also explain our fascination with space. Humans have always looked at the stars with wonder, but in the modern era, that wonder has become an obsession. We spend billions of dollars on space programs. We risk lives to go to the moon, to build space stations, to send probes to distant planets. We talk seriously about colonizing Mars, about building cities on other worlds, about becoming a multi-planetary species. No other survival imperative fully explains this drive. Space is expensive, dangerous, and offers no immediate resources that we could not obtain more easily on Earth. Yet we pursue it anyway, driven by something deeper than logic. Could this be genetic memory? A faint echo of a time when leaving a dying world was not a fantasy, but a necessity. The concept of genetic memory is controversial in science. Genes encode proteins, not experiences or knowledge. Memories are stored in neural connections, not in DNA. But genes do influence behavior. They shape instincts, drives, preferences. A species that survived through migration might carry genetic predispositions toward exploration, toward risk-taking, toward looking at distant horizons and feeling not fear, but possibility. These predispositions would not be conscious memories. They would be urges, feelings, patterns of behavior that feel natural even when they are not rational. And humans, more than any other species, seem driven by such urges. There is also the recurring theme in human culture of a lost homeland. Myths from around the world speak of an original paradise from which humanity was expelled or which was destroyed. The Garden of Eden, Atlantis, Avalon, Shangri-La. These are stories of places that once existed and were lost. They are usually interpreted as metaphors, but what if they preserve a fragment of actual memory? If humans are descended from Martian refugees, the memory of that lost world might have been passed down through generations, gradually transforming from history into mythology. The details would have been lost or distorted over thousands of years, but the emotional core would remain. We came from somewhere else. We lost that place. We can never go back. This theme appears not just in Western cultures, but in indigenous traditions worldwide. Australian Aboriginal Dreamtime stories speak of a creative period when the world took shape, a time fundamentally different from the present. Native American traditions include stories of emergence from previous worlds or underground realms. Hindu cosmology describes cycles of creation and destruction spanning billions of years, where entire worlds rise and fall. These are not usually interpreted as literal history, but as spiritual or philosophical teachings. And perhaps that is all they are. But it is striking how universal these themes are, how consistent across cultures that had no contact with each other. Could they all be drawing on the same deep well of memory? A collective human understanding that our story did not begin here. The idea of collective memory is another controversial concept. Psychologist Carl Jung proposed the existence of a collective unconscious, a layer of the human psyche shared by all people, containing archetypes and symbols that appear across cultures. Jung's ideas have been influential in psychology and mythology, but they remain outside the mainstream of cognitive science, which tends to explain cultural universals through shared human experiences rather than inherited memory. Still, if humans do carry some genetic heritage from Martian ancestors, it is not unreasonable to suggest that certain deep patterns, certain ways of thinking and feeling, might have been passed down. Not as specific memories, but as predispositions, as structures of consciousness that shape how we interpret the world. Now let us turn to a different kind of evidence, one that is more concrete, but also more controversial. There are researchers who claim to have found artifacts on Mars itself, visible in photographs taken by rovers and orbiters. These claims are almost universally rejected by the scientific community, dismissed as examples of pareidolia, the tendency to see meaningful patterns in random data. But some of these images are genuinely puzzling, and it is worth examining a few of them critically, not to prove they are artificial, but to understand why they continue to generate debate. One of the most discussed images shows what appears to be a perfectly rectangular formation on the Martian surface. The edges are straight, the corners are right angles, and it sits on the surface in a way that does not immediately suggest natural formation. Skeptics point out that natural processes can create straight lines and right angles, particularly through fracturing and erosion along crystal planes. Rock formations on Earth sometimes exhibit similar geometry. Without closer examination, without the ability to study the object up close and determine its composition and structure, it is impossible to say definitively whether it is natural or artificial. But the fact that such formations exist on Mars is significant. If a civilization once existed there, and if they left structures behind, those structures would likely be severely eroded after billions of years. They would not look like pristine buildings. They would look like weathered rocks, barely distinguishable from natural formations. The only way to identify them would be through subtle clues, through patterns that are just slightly too regular to be coincidental. Another image shows what some have interpreted as a carved face, different from the famous face on Mars, but equally provocative. The formation has features that resemble eyes, a nose, and a mouth, though, like the original face, higher resolution images might reveal it to be entirely natural. The question is not whether this specific formation is artificial, but whether we are looking at Mars with the right mindset. If ruins exist, we might be photographing them constantly without recognizing them for what they are. Then there are the spheres. Mars rovers have photographed numerous small spherical objects on the surface, ranging from a few millimeters to several centimeters in diameter. Scientists call them blueberries, and they are explained as concretions, mineral deposits that form in the presence of water. This explanation is almost certainly correct for most, if not all of them. But the existence of natural spheres raises an interesting question. If artificial spheres, ball bearings, ornaments, or other manufactured objects also existed on Mars, how would we distinguish them from natural concretions? After billions of years of exposure, any metal or composite material would have oxidized and eroded. An artificial sphere would end up looking very much like a natural one, composed of iron oxide or other minerals, with no obvious signs of manufacture. This is the fundamental problem with searching for artifacts on Mars from photographs. We are looking at a world that has been weathered for an immense span of time, where almost everything has been broken down and transformed. Distinguishing artificial from natural in such conditions is extraordinarily difficult. It requires not just looking at individual objects, but at patterns, at context, at statistical anomalies that suggest deliberate arrangement or construction. And that kind of analysis requires far more data than we currently have. We need higher resolution images covering more of the planet's surface. We need ground truth, actual samples that can be analyzed in laboratories rather than interpreted from pixels. Most importantly, we need humans on Mars, geologists and archaeologists who can examine formations in person, apply centuries of experience in distinguishing natural from artificial, and make judgments that robots simply cannot. This is one of the strongest arguments for sending humans to Mars. Not just for science, not just for exploration, but because some questions can only be answered by having people there on the ground, using their eyes and their experience to interpret what they see. Robots are valuable, but they have limitations. They cannot adapt to unexpected situations the way humans can. They cannot make intuitive leaps or recognize patterns that their programming was not designed to detect. If evidence of a past civilization exists on Mars, there is a real possibility that rovers have already photographed it, but the images sit in archives, categorized as geological features, waiting for someone with the right perspective to look at them again and see what was missed. This has happened before in science. Astronomical photographs taken decades ago have been reanalyzed with modern techniques and revealed objects that the original observers never noticed. Archaeological sites have been discovered by looking at old aerial photographs with fresh eyes, seeing patterns that were invisible to earlier viewers. The data from Mars is accumulating constantly. Thousands of images, millions of measurements, petabytes of information stored in databases. Most of it has been analyzed for specific scientific purposes, looking for signs of water, studying mineralogy, understanding climate history. But how much of it has been examined for signs of artificiality? How many images have been looked at by someone asking not, what natural process created this, but could this possibly be artificial? The answer is very few. And this is not because scientists are closed-minded, but because the question seems so improbable that it is not worth the time. When you have limited resources and endless questions to investigate, you focus on the ones most likely to yield results. Searching for alien artifacts seems like a waste of effort when there is so much basic science still to be done. But as our understanding of Mars improves, as we map more of its surface and learn more about its history, perhaps the time will come when this question deserves more serious attention. Not as speculation or fantasy, but as a legitimate scientific inquiry. If Mars was habitable for hundreds of millions of years, and if life there had the same potential to evolve into complex forms as it did on Earth, then the possibility of past civilization is not absurd. It is unlikely, yes, but unlikely is not the same as impossible. And in science, we investigate unlikely possibilities all the time, because sometimes they turn out to be true. Consider the example of the Higgs boson. For decades, it was a theoretical particle predicted by equations but never observed. Many physicists doubted it existed. The experiments required to detect it cost billions of dollars and required technology at the absolute cutting edge of what was possible. But the search continued, driven by the understanding that if the Higgs boson did exist, finding it would be one of the most important discoveries in physics. And eventually, it was found, confirming theories and opening new areas of research. The search for evidence of Martian civilization might follow a similar path. It seems improbable now, a fringe idea that most scientists do not take seriously. But as our technology improves, as our presence on Mars becomes permanent rather than temporary, we will have the tools to investigate more thoroughly. And if evidence exists, even in the most degraded and ambiguous form, we will eventually find it. The question is, are we ready for what that would mean? If definitive proof emerged that a technological civilization once existed on Mars, the immediate scientific impact would be enormous. Every assumption about the uniqueness of life, about the rarity of intelligence, about humanity's place in the cosmos would have to be reevaluated. But beyond the science, there would be profound philosophical, religious, and cultural implications. Religious traditions around the world would face difficult questions. If humans are descended from Martians, what does that mean for creation stories that place humanity's origin on Earth? How do we reconcile ancient scripture with the possibility that our ancestors came from another planet? Some religious thinkers might argue that divine creation could have occurred on Mars just as easily as on Earth, that the location does not change the fundamental relationship between humanity and the divine. Others might see the Martian origin as confirmation of their beliefs, pointing to ancient texts that speak of beings descending from the sky or humans being placed on Earth by higher powers. Still others might reject the idea entirely, seeing it as incompatible with faith. These debates would not be easily resolved, and they would have real consequences for how people understand their identity and purpose. Culturally, the confirmation that we are not native to Earth would be both unsettling and liberating. It would undermine the sense of belonging that humans have always felt to this planet, the idea that we are children of Earth, shaped by its environments and ecosystems. But it would also expand our identity beyond a single world. We would be citizens of the solar system, with roots on 2 planets. This might make the project of space exploration feel less like leaving home and more like returning to it, reconnecting with a heritage that was lost. Politically, the discovery could have unpredictable effects. If all of humanity shares a common Martian ancestry, it might foster a sense of global unity, breaking down the divisions of nationality, race, and culture that have caused so much conflict. We would all be Martians, descendants of the same refugees, heirs to the same lost world. This could be a powerful force for cooperation, particularly in addressing challenges like climate change that require global action. On the other hand, it might create new divisions. Some groups might claim closer genetic ties to the Martian ancestors, using pseudoscientific arguments to justify supremacy. Others might reject the Martian connection entirely, clinging to an Earth-centered identity. The same discovery could be used to unite or to divide, depending on how it is interpreted and presented. Then there is the question of responsibility. If Mars was once inhabited, and if those inhabitants destroyed their world or failed to save it, do we have an obligation to restore it? If we are their descendants, does that give us a special claim to Mars? A right to terraform it and make it habitable again? Or would that be a desecration, erasing what remains of their world to suit our needs? These are not easy questions, and they touch on issues of ethics, property, and heritage that have no clear answers. Some would argue that Mars is a dead world, that whatever civilization existed there is gone, and that we have every right to use it as we see fit. If we can make Mars habitable, if we can create an environment where human life can flourish, that is an act of creation, not destruction. We would be bringing life back to a world that lost it, continuing the story that ended billions of years ago. Others would argue that Mars should be preserved as it is, a monument to a lost civilization, a place of historical and archaeological significance that should not be altered. Just as we protect ancient ruins on Earth, recognizing their value as connections to our past, We should protect Mars as a connection to a past that might be even older and more significant. Terraforming, in this view, would be like bulldozing the pyramids to build a shopping mall. It might be technically possible, but it would be a loss of something irreplaceable. Finding a balance between these perspectives will be one of the great challenges of the coming centuries. As we develop the capability to alter entire planets, we will need to think carefully about the ethical implications of doing so. Mars will be the test case, the first world beyond Earth, where we must decide whether to preserve or transform, whether to study or settle, whether to honor the past or build the future. And underlying all of these decisions will be the question of connection. If Mars was our ancestral home, if we carry within us genetic and cultural memory of that world, then our relationship to it is not simply one of scientific curiosity or economic opportunity. It is personal. It is about identity, about understanding where we came from and what that means for who we are. This brings us to the final and perhaps most important aspect of the theory. If humans are descended from Martians, it changes how we think about our future, not just on Mars, but in the wider universe. One of the greatest questions facing humanity is whether we will remain confined to Earth or become a spacefaring species, spreading throughout the solar system and eventually to other stars. This question is often framed in practical terms, about technology, economics, and resources. But it is also a philosophical question, about who we are and what we are meant to do. If we are native to Earth, evolved here over billions of years, then leaving might feel like an abandonment, a rejection of our home in favor of cold, hostile environments where we do not belong. It might seem unnatural, a violation of our place in the ecological order. But if we are descended from Martians, if our ancestors already made the journey from one world to another, then space travel is not an aberration. It is what we do. It is encoded in our history, perhaps even in our genes. We are a species that has already survived planetary migration once. Doing it again is not unprecedented. It is a continuation of a pattern that began billions of years ago. This perspective makes the colonization of space feel less like a radical departure and more like a homecoming. Returning to Mars is not conquering a new world, but reclaiming an old one. Settling other planets is not an act of hubris, but an act of continuity, following in the footsteps of ancestors who faced the same challenges and made the same choices. It reframes space exploration not as a luxury or a distraction from problems on Earth, but as an essential part of human identity, something we must do because it is who we are. This does not mean that space colonization is inevitable or easy. The challenges are immense, the distances are vast, the environments are lethal. Many people will die in the attempt, colonies will fail, resources will be wasted, there will be setbacks and tragedies. But if history teaches us anything, it is that humans are persistent. We attempt the impossible, fail, learn, and try again. We cross oceans in fragile boats, climb mountains that kill more people than they allow to reach the summit, explore polar regions where survival seems impossible. We do these things not because they are practical, but because they call to something deep within us. If that calling is the echo of Martian ancestors who once faced the same existential threat we face now, then perhaps it is not just stubbornness or curiosity that drives us. Perhaps it is memory. Now, let us consider what the discovery of our Martian origin would mean for the search for life elsewhere in the universe. One of the core assumptions in astrobiology is that life is rare, that the conditions required for its emergence are so specific and so unlikely that most planets remain sterile. This assumption is based largely on the fact that we have only one confirmed example of life: Earth. If Mars also had life, especially if it progressed to complex forms, that would double the known instances of life in the universe. And if that life is connected to Earth, if we are descended from it, then it suggests that life, once it emerges, is resilient enough to spread, to survive transfers between worlds, to persist across billions of years. This would have profound implications for how we search for life on other planets. It would suggest that life is not confined to the world where it originated, but can propagate through a solar system, carried on meteorites, or deliberately spread by technological species. If this happened between Mars and Earth, it could happen in other solar systems as well. Moons like Europa or Enceladus, which have subsurface oceans and receive material from their host planets through impacts, might harbor life that originated elsewhere in their system. Planets in other star systems might exchange life through the same mechanisms, particularly in densely packed systems where planets orbit close to each other. The universe, in this view, is not a collection of isolated biological experiments, each starting from scratch, but a web of connections, where life that emerges in one place can seed many others. This makes the search for life both more hopeful and more complicated. More hopeful because it suggests life might be more common than we thought, spreading beyond its point of origin. More complicated because it means that finding life on another world does not necessarily mean that life evolved there independently. It might be a transplant, carried from somewhere else, just as Earth life might be a transplant from Mars. This brings us to the Fermi paradox, one of the most perplexing questions in science. If intelligent life is common in the universe, and if technological civilizations arise frequently, then where is everyone? Why do we not see evidence of alien civilizations? Why have we not detected their signals, found their probes, or encountered them directly? Many solutions have been proposed to the Fermi paradox. Perhaps intelligent life is extremely rare. Perhaps technological civilizations destroy themselves before they can spread. Perhaps they are out there but too far away for us to detect. Perhaps they are hiding, deliberately avoiding contact. Or perhaps they exist in forms we do not recognize, using technologies we cannot detect. The Martian hypothesis offers another possible solution. If civilizations commonly arise on planets that are habitable for only a limited time, and if those civilizations either die out or migrate to younger worlds, then at any given moment, most life-bearing planets might be in between civilizations. They might have fossil records, might even have living ecosystems, but no active technological presence. This would make the universe seem emptier than it actually is, because we are looking for signals from civilizations that exist now, not evidence of civilizations that existed in the past. On a cosmic timescale, civilizations might be like fireflies, blinking on briefly and then fading, with long, dark intervals between flashes. If we only look for the light and ignore the darkness, we miss most of the story. This perspective suggests that the search for extraterrestrial intelligence should focus not just on radio signals or artificial lights, but on archaeological evidence, on planets that show signs of past habitability and might carry relics of extinct civilizations. Mars is our first opportunity to conduct such a search. If we find evidence there, it will tell us that dead civilizations are detectable, that their traces can survive geological time, and that we should be looking for similar traces elsewhere. If we find nothing, it might mean that civilizations truly are rare, or that their traces are too subtle for us to recognize. Either way, Mars will be the test case that shapes how we search for life beyond our solar system. Let us now return to the present and ask a practical question. If the theory that humans are descended from Martians has any validity, what should we be doing about it? The answer, in some ways, is already being done. We are sending missions to Mars, studying its geology, searching for signs of past life. But we could be doing more. We could be explicitly searching for evidence of past civilizations, not as a fringe activity, but as a legitimate scientific goal. This would require a shift in perspective among the scientific community, a willingness to take the possibility seriously enough to dedicate resources to it. It would mean designing missions specifically to search for artifacts, for unusual chemical signatures, for patterns in the landscape that might indicate artificial structures. It would mean developing new techniques for analyzing images and data, using artificial intelligence and machine learning to identify anomalies that human observers might miss. And most importantly, it would mean sending humans to Mars, equipped not just with scientific instruments, but with archaeological training, so they can investigate features that might be ruins, applying the same methods that have uncovered ancient civilizations on Earth. This is a long-term project, one that will take decades or even centuries to complete. But if the payoff is understanding our true origin, confirming that we are part of a lineage that spans 2 worlds and billions of years, then it is worth the effort. The knowledge would be transformative, changing how we see ourselves, how we approach space exploration, and how we understand our place in the universe. It would be the most important discovery in human history, proving that we are not alone, that we have never been alone, and that our story is far older and grander than we imagine. In the meantime, we continue to explore Mars with robots, each new mission adding pieces to the puzzle. The Perseverance rover is currently searching for signs of ancient microbial life, collecting samples that will eventually be returned to Earth for detailed analysis. The Ingenuity helicopter has proven that flight is possible in Mars's thin atmosphere, opening possibilities for future aerial exploration. The European Space Agency, China, and other nations are planning their own missions, expanding the scope and scale of our investigation. And NASA, along with private companies like SpaceX, is working toward the goal of sending humans to Mars within the next few decades. When those first astronauts land, when they step out onto the red surface and look around at a landscape that might once have been home to their distant ancestors, they will carry with them the hopes and questions of all humanity. They will be explorers, scientists, and perhaps, without knowing it, descendants returning to a world their forebears left behind billions of years ago. What they discover will shape the future of our species. If they find nothing, if Mars proves to be exactly what it appears, a dead world that never harbored more than simple microbes, then we will know that Earth is special, that our journey is unique, and that we bear the full responsibility for preserving the only known instance of technological civilization in the universe. But if they find something, if they uncover evidence that Mars was once alive with complex life or even civilizations, then everything changes. We will know that we are part of a larger story, that our origin is not confined to one world, and that the future of humanity lies not just in protecting Earth, but in spreading throughout the cosmos, continuing a journey that began long before we existed. This is the power of the question. It is not just about Mars. It is about us, about who we are, where we came from, and where we are going. And until we have answers, until we have explored Mars thoroughly enough to say with certainty what happened there, the question will remain, haunting and compelling, calling us to return to the red planet and discover the truth.